Hello everyone, this is our second lecture for Chapter 9, an introduction to hypothesis testing. In this lecture video, we will discuss alpha, also known as significance level. We will also talk about effect size. We've talked about the first step in hypothesis testing, state the hypotheses. I want to quickly review and add a few things I forgot to mention in the previous video. Remember that there are two types of hypotheses, null and alternative, also known as research hypotheses. The null hypothesis H0 always specifies a single value. It has the equals sign in it somewhere. It states that nothing happened. There is no difference. Chance is a good explanation for our results. And our sample statistic is not different from our hypothesized population parameter. The null hypothesis in general is something we do not want to find support for. However, there are some exceptions. For example, H0, the null, there is no difference between men and women in performance of military tasks, is a null we would want to find support for. The alternative hypothesis H1, also known as the research hypothesis, always specifies a range of values. It has an inequality in it somewhere. It states that something happened. There is a difference. Chance is not a good explanation for our results. And our sample statistic is significantly different from our hypothesized population parameter. The alternative hypothesis, in general, is something we want to find support for. However, there are some exceptions. For example, the alternative H1, there is a difference between men and women in performance of military tasks, is an alternative we would not want to find support for. In our last video, we used the example of testing whether preschool children in the U.S. watch 3 hours of TV per week. Our null hypothesis is H0, mu equal to 3 hours. And our alternative hypothesis is H1, mu not equal to 3 hours. Let's say we draw a sample of n equal to 100 preschool children and get a sample mean of m equal to 5 hours. Which hypothesis, the null or the alternative, describes the population? If we were to draw another sample of n equal to 100 preschool children, would we be guaranteed the same sample mean of m equal to 5 hours? Remember, sampling error is the variability of sample statistics from sample to sample. We would not expect the same sample means if we selected more samples of n equal to 100 preschool children. So the big question is the variation we found due to sampling error or some real or systematic variability? The unsettling answer is that you decide on the odds for casting your decision in favor of H0 or H1, the null or the alternative. Even after you decide, you're still never sure you made the right decision. All your choices are based on probability distributions or sampling distributions, so you never say or use the word prove in this class or when you provide your conclusions. The second step of hypothesis testing is to set the criteria for a decision. Remember that we have to decide whether to reject the null hypothesis or not reject the null hypothesis. A decision to reject the null means we have sufficient evidence for the alternative hypothesis. A decision to not reject the null means we do not have sufficient evidence for the alternative hypothesis. The sampling distribution of sampling means is divided into two regions. The region with sample means that are likely if the null hypothesis H0 is true, and the region with sample means that are very unlikely if the null hypothesis H0 is true. This second region is known as the critical or rejection region. So we need to determine at what point or level is this critical region. This point or level will determine the rejection region, or the set of extreme sample means that will lead to the rejection of the null hypothesis H0. To set the criteria for a decision, we state the level of significance or rejection level, also known as alpha, for a hypothesis test. The significance level is an expression of how rare your results are if the null hypothesis is true. It is usually expressed as a p-value, and the lower the p-value, the less likely the results are due to chance or sampling error. The p-value is the probability of finding the observed or more extreme results when the null hypothesis is true. Alpha is a p-value used to define very unlikely events or outcomes. Alpha is also the probability that you will reject the null hypothesis H0 when it is in fact true. More on this when we discuss decision errors. Sometimes alpha will be given to you on tests, homework assignments, or by journal editors. Other times, you will have to choose alpha yourself. However, for this class, you will always be provided with alpha. Typical alpha levels are 0.05 or 5% and 0.01 or 0.1 or 1%. The boundaries for the critical or rejection region or area are determined by alpha level. A cutoff score is the critical value that separates a certain area under the normal curve. Z-scores are cutoff scores or critical values. In Chapter 10, we will introduce T-critical values that also act as cutoff scores. These cutoff scores are what separate the two regions we talked about earlier, the region with sample means that are likely if the null hypothesis H0 is true, or what we like to call the non-rejection region, and the region with sample means that are very unlikely if the null hypothesis H0 is true, or what we call the rejection region. The p-value approach is what you will be using when you calculate z-scores. The reason for this is that we can look up actual probabilities in the standard normal table and provide these probabilities when we are reporting the results of our hypothesis test in our conclusions. The p-value is the calculated probability of getting a test statistic at least as extreme as the one observed if the null hypothesis is true. It is determined by calculating the test statistic using z-score formula and then determining the associated probability. If the p-value is less than alpha, which sets the size or area of the rejection region, then the null hypothesis is rejected. So if p is less than alpha, we reject the null, H0. If p is greater than alpha, then we do not reject the null, H0. A hypothesis test evaluates the statistical significance of the results from a research study. There are concerns about hypothesis tests, even though they are commonly used. These concerns are: the focus of the hypothesis test is on data, not the hypothesis, and significant results are not always substantial or all that important. In other words, Just because we got a significant result, it does not necessarily mean that we have a large effect. The hypothesis test is influenced not only by mean differences, but also by the size of the sample. So, even a very small effect can be significant if it is observed in a very large sample. We could find any difference in a large enough sample. And so we use effect size to measure the magnitude of an effect regardless of sample size. The effect size gives us what we call the practical significance of the results. Effect size will also determine whether or not we will get similar results if we replicate the study. Smaller effect sizes will make it difficult to replicate results, while larger effect sizes will make it easier to replicate the results. We use Cohen's d as a standardized measure of effect size. Here is a chart to help you determine the magnitude of an effect. An effect size d equal to 0.2 is considered a small effect. An effect size d equal to 0.5 is considered a medium effect. And an effect size d equal to 0.8 is considered a large effect. Much like a z-score, Cohen's d measures the size of the mean differences in terms of the standard deviation. So for individual scores, Cohen's d equals x minus the population mean mu divided by population standard deviation sigma. And for sample means, Cohen's d is equal to sample mean m minus population mean mu divided by population standard deviation sigma. I want to add one quick thing. With Cohen's d, or effect sizes, because these are magnitudes, Cohen's d is never a negative number. And so we remove the negative if there is, when we do the calculation, when we do this formula, if there is a negative, we just remove it and we report out a positive Cohen's d, always. In our next video, we will discuss decision errors and power.